Okay, so looking at graphing rational functions, some more challenging ones than we did in our book. So anytime we have a function of this form, where we have a numerator and a denominator, as long as these are polynomials and not exponentials or something else like that, we're going to have what's called a rational function. The domain is always going to be whatever does not make this denominator 0. So 1 does make it 0. So 1 is not going to be in our domain. That's stuff we've already done. The asymptotes that a graph can have are vertical, which we've talked about, horizontal, which we've talked about. This is a new type, slant asymptotes. A slant asymptote is going to look like this, exactly what you would think, a slanted line. Okay? And we might have a vertical asymptote. So it would look something like that. It's going to be a new concept for us. The horizontal asymptote tells us what value the graph gets closer and closer as x goes down to infinity or negative infinity. Here's the other new thing, is that if there's a common factor in the numerator and the denominator, then the graph will have a hole at that point. It will not be a vertical asymptote. Let me show you what I'm talking about there. Suppose I have y equals x minus 2 over x minus 2. If you were to graph that, this is what you would actually see on your calculator. Why do you think you would see that? Yeah. If I do x minus 2 divided by x minus 2, I get y equals 1, don't I? So this is actually the line y equals 1. But based on what we've talked about, wouldn't you have looked at that and thought, oh, there's a vertical asymptote at x equals 2? Well, not if it cancels out. What happens is we get this function y equals 1, but there would be a hole in the graph. The hole would be at, what makes this equal 0? 2, comma 1. So right here, there would be a little hole in the graph. The calculator can't show that, but we will be showing that. So just be aware. Yeah? Yeah, it's a limit as we get closer and closer. It's that limit concept. Okay, so the first thing here, the graph of a rational function is a vertical asymptote for each real 0 of the denominator. A graph will never cross the vertical asymptote. We've talked about that. The graph of a rational function has at most one horizontal asymptote. We can cross horizontal asymptotes. That can happen. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is going to be our horizontal asymptote. That's important. Let that kind of sink in. When the degree of the top is less than the degree of the bottom, y equals 0 is a horizontal asymptote. Can somebody give me a function that would have a horizontal asymptote of y equals 0? Just make the degree on top less than the degree on bottom. X minus 5 over what?
X squared plus 2x.
Sure. As soon as you say x minus 5 and x squared, right there you go. You got it. Okay, good. If the degree of the top is equal to the degree of the bottom, then the line y equals a over b is a horizontal asymptote, where a is the leading coefficient of the top and b is the leading coefficient of the bottom. All right, that sounds confusing, but look at your first warm-up. Our first warm-up problem was this. We used to find the horizontal asymptote by doing what? Dividing, right? We would do dividing. And if I do division, I would do negative 5 into 2 and negative 1. I can actually do synthetic on this. I'm doing synthetic. So I would bring this down, I get to, I'd multiply, and I don't even care about this. This tells me that y equals 2 would be the horizontal asymptote. Can you see how all I have to do is 2 divided by 1 and I get it? All right? So what if I change this to a 2 down here as well? Now what's the horizontal asymptote? Y equals 1. Good. What if I change this to a 5? What is it? 5 halves. That's all you have to do. So when those degrees are the same, we just look at these numbers and divide. All right, last case. What about if the degree of the top is greater than the degree of the bottom? Well, then we have no horizontal asymptote. And what happens is this. We get what's called a slant asymptote. That thing I was talking about up there. This is going to happen when the degree of the top is 1 more than the degree of the bottom. And it says divide the top by the bottom to get the equation of the slant asymptote. All right, so we're going to look at this one down here right now. Can you see how the degree on the top is 1 greater than the degree on the bottom? So it has to have a slant asymptote. All right, we can do this 2 ways. I'm going to show you both. You can do x minus 4 divided into x squared plus 0x plus 1. I'm doing the top divided by the bottom. X squared divided by x is x. I multiply. I subtract, and I get 0 and 4x. 4x divided by x is 4. 4 times x is 4x. And now I can even stop. I don't care. See how I get x plus 4? Right there is our slant asymptote. Here the slant asymptote is y equals x plus 4. The other way I could have divided this is with synthetic. What's a number that makes this equal 0? So I do 4 into, look at the top, 1, 0, 1. I bring this down, I multiply and add. I can stop. That's just going to give me the remainder. See how this still gives me y equals x plus 4? So either way. So you guys can do these problems either way on finding the slants. If this power is 1 more than that, I divide to find the slant asymptote. What is the vertical asymptote? What makes the bottom 0? 4. Okay, so on this section, all we're doing is finding the asymptotes. To find the asymptotes, you want to factor first. This factors down into x plus 2 and x minus 2. Whatever makes the bottom 0. Now we can have more than one vertical asymptote. So what are they going to be? Right. Now, what about as far as slant or horizontal? Brad, what do we have? A slant, horizontal? We do. Do you know what it is? You are correct. Do you know why?
Because there's no number to the right being added.
Okay. I would look at the powers. I'd say the powers instead. So this power is greater than that one. So when the bottom power is higher, it's always going to be 0. All right. What about the next one? We're going to factor. Okay. Ainsley, can you tell me the vertical asymptotes now? Good. Okay, and then what about for the horizontal? Does anybody know what that would be, remembering what we did up above? What is it? Yeah. Right. How did you know that? Right, the powers are the same, so we divide the leading coefficients. Okay, let's look at the next one because there's a bit of a trick here. I'm factoring the bottom. Does anybody know what the trick is that I was... Yeah, Brad, what is... Right, so that is not a vertical asymptote. Okay? because it canceled with the numerator. So we only have one vertical asymptote on this at 3. Okay, what about the powers? Well, the power's higher on bottom. Anybody know what that means? Higher on the bottom? Y equals 0. Good. Okay, and then we have one more. The vertical asymptote. Kanaya, what is it? What makes the bottom 0? Good. And what about horizontal or slant? Which one do we have? Slant is right. Crazy, how do I find that? Okay, you want to use synthetic or long? Okay, so I'm going to do 4. I'm going to use my coefficients of x squared, my coefficient of x, and my constant. I'm going to bring this down. I'm going to multiply and add. That's a remainder, so I'm going to stop. And so the slant asymptote is going to be y equals 3x plus 12. Yeah, but now we're going to look at how to apply it. Okay, so flip over on the back. We're just going to do these top 2. How do we apply this? Well, what we want to be doing, our ultimate goal is to be able to graph using all these new rules. So it says for each of the following, identify all asymptotes. State the domain, range. We're not actually going to do range, so you can mark out range. We're going to find the x and y intercepts. Also, if the function crosses its horizontal asymptote, state where that occurs. What did I say we should always do first? Simplify by factoring. Factor out a 4. Factor the denominator. So do I have 2 vertical asymptotes? Yes or no? No, because why? These cancel. So instead of having a vertical asymptote, this is my new function I'm going to be using. I don't have a vertical asymptote there. I have a hole at, what is it that makes that be 0? No, this one. -1. Plug that back into this. So 4 over -1 minus 2 is -3. See, I'm plugging -1 into my function. So here's where the hole will be. And I'm going to graph that here in just a minute. Vertical asymptote. Logan, do you know where the vertical asymptote would be? Whatever makes that denominator 0. X equals 2. So I'm going to kind of start graphing as I go. So I'm at x equals 2. I also know there's a hole in the graph at -1, -1 1/3 right there. Make that a hole in the graph. I'm now going to find my intercepts. I always like to do all of that before I do the domain. So to find an x-intercept, I have to plug in 0 for y. So I'm going to take this function right here, and I set it equal to 0, because I'm letting y equal 0. If I cross multiply, I'm going to get 4 equals 0. Can I solve that? No. So there's no x-intercept. None. For the y-intercept, we plug in 0 for x. If I plug 0 into this function, what do I get? -2. So I know that's going to be a point on my graph. Now, is it ever going to cross this horizontal asymptote? Well, actually, let's state the horizontal asymptote. I forgot to state that. Look at the power. The power on top is less than the power on bottom. What is the horizontal asymptote? 0. So here's our horizontal asymptote. We are not going to cross that horizontal asymptote because we don't have any times when y can equal 0. Remember, we just tried that and it didn't work. So I know the function's not going to go above here. So now I know what it looks like. It's going to come up like this, not cross it. It's going to come down like this. Now, go ahead. Yeah.
So if we have a hole, then it's always going to go through it.
Yeah, it's going to get really close to it. It really doesn't go through it. See how I kind of left it open? And I'll show you that here in just a minute when we check. The thing with these is that now this function, it doesn't have to be symmetric like it used to be. It doesn't have to be this hyperbola up here. It could go down here because we have more complicated graphing that we're doing. So I have to check a point. I'm going to check a point over here, like 4. If I plug 4 in, all I care about is whether it's positive or negative. If I plug 4 in, what do I get? 2. So at 4, we're going to be at 2. So because that's positive, I know it's going to have to look like this. The last thing we have to do is state our domain, and this is a little tougher than you may think. We'll get to that in just a minute, but first I want to show you how we can check it. I've already put it into the calculator, so just kind of watch. Oops, no I didn't, I lied. Let me put it in. So you have to use parentheses if you have one of these older calculators. If you have a newer one, you don't have to worry about it. We put in the original function. I got to say do the whole numerator divided by the whole denominator. I'm going to graph it, and here's the way it looks. So we can see it looks very similar. Now I want you to look at this for a minute. When I look at my table of values, can you see right here, look at that, error. Why would it be that at -1 it's giving me an error? What happens at -1? There's a hole, right? Also, look what happens at 2. Why are we getting that error? The vertical, well, no, not because of the reflection of that. The vertical asymptote is what's causing that. Okay, now remember, domain means all the x's I can use. So can somebody tell me the domain then? It's tougher than what we did last night. Go ahead, Nate.
Negative infinity to -1.
Good.
And then -1 to 2. Union to infinity.
Very good. Because, guys, we're not allowed to use that -1 where that hole is. Okay? So you got to watch that. Yes?
So how do you know to use the hole at -1 to find the...
Because that's what makes this not work. Like if I plugged -1 in here, watch what happens. 4 times -1 is -4 plus 4 is 0. If I plug -1 down here, I get 1 plus 1, that's 2, minus 2, that's 0. See how 0 over 0 has no meaning? So that's how I know that there's a hole. When x is -1, they canceled out. So when they cancel out like that, whatever makes that 0, that's not a vertical asymptote, it's a hole. And then to find this value, I had to plug -1 over into this simplified version. Okay? Any other question on this type? All right, let's go down to the next one. First thing we want to do is factor that denominator. Okay, so let's go ahead. Do we have any holes in the graph? No. Vertical asymptote? Everybody should be able to give it to me. What is it? Yep. And let's go ahead and graph that as we go. Okay. I now like to find the horizontal asymptote. Look at those powers. What's it going to be, guys? 0. So I'm going to go ahead and plot that. Now I'm going to find my x-intercept. To do that, I'm going to plug in 0 for y. Right there's y. So I plug in 0 for y. I cross multiply. What do I get then? -3. So -3, 0 is going to be an x-intercept. Is it going to cross my horizontal axis asymptote then? Yeah, because it's right there on that horizontal asymptote, so it's going to cross it. Remember how we said it can cross it. By setting this function equal to the horizontal asymptote, I can see that it's crossing it. Right there. Find the y-intercept. Plug in 0 for x. What do you get? -3/4, right? Just plugging in 0. 3 over -4 is -3/4. So we got that point. All right. So those are the only points we know, and we have to know what's going on with this graph. Well, this graph can come down like this, or it could come up like this. I need to know right here, is it positive or negative? That kind of stinks because that point's hard to check. If that point is like -2.5. So I have to plug -2.5 in. F of -2.5. -2.5 plus 3, that's going to be positive. All I care about is whether it's positive or negative. 2.5 squared, well 2.5 squared is more than 4, because 2 squared is 4. So I know that's going to be positive. So I know that this has to be something positive. So now I know which direction it comes. It has to go like that. I'm trying to give you shortcut ways so you don't have to spend so much time plugging in. Now, here, it could go up like this or it could go down. How do I know that it goes down? Without checking a point? Yeah. Go ahead. Do you know, Ryan?
Because of the square factor?
No, that's not really the reason why. Anybody know? What? Okay, kind of. Nate?
Would you just put the x's and y's? So you go, or no, it's like the opposite kind of thing.
It has to do with this, guys. There's only one x-intercept. So if there's only one x-intercept, can it go up like this?
No.
No, because there's no more x-intercepts. There's just that one. So I know it has to go down like this. And this is going to have to go down like this. Because there's no other x-intercepts. What else? What if I didn't realize that? What could I do? Just check the point, right? I could check -1. Check and see. What's that value? Let me just show you that way. If I check -1, -1 plus 3 is 2. -1 squared is 1. Minus 4 is -3. So see how that's just about right? You know, I went maybe down a little too far, but it's still negative, so it's going down. Okay? Yeah.
How can you call the horizontal asymptote at 0 as an asymptote if it's being crossed?
Because a horizontal asymptote just tells you what's happening at the end. It tells you that as this x goes out and out, it's going to approach 0. And the same thing's going to have to happen here. It's either going to come out here and approach 0, or it's going to come out here and approach 0. That's all a horizontal asymptote does, is it tells you the end behavior of the graph. It tells you what's happening at the ends. Okay. How can I quickly check, guys, whether it's up here or down here? I know it doesn't cross down here. So what do? Check a number, right? What's a number down here? An x value down here? 5, okay. So I'm going to do f of 5. If I plug in 5, 5 plus 3, that's positive. 5 squared is 25 minus 4, that's positive. So is it positive or negative? Positive, I know it has to be up here. I don't even care if it's exact. We're getting general shapes for these. I want you to see how this looks. Make sure you have the whole numerator in parentheses and the whole denominator. Here's how it looks. Okay? It doesn't show us those asymptotes, those vertical asymptotes, but see how we're really close in the way that that looks. Doesn't have to be exact, just general idea of the shape. And here's what I'm talking about here, Bryce. I'm glad you asked that question. Watch when I hit trace. Okay, I'm going way down here. Look at these X values. They're getting smaller and smaller. And I'm just holding this button down. Can you see how the Y is just getting closer and closer to 0 as I hold that button down? That's what a horizontal asymptote is. It's what is the function getting closer to. And if I sit here and hold it until the bell rings, I don't think it's ever going to show 0 exactly, because it's never allowed to cross it again. We only have that one x-intercept. I could, see how it's getting closer, but that's what an asymptote is. It can't cross it again because we only had the one x-intercept. Okay? You get the general idea? This is just an extension. We're going to have more vertical asymptotes. We're going to have to deal with the horizontals more now. Another thing, guys, I want to explain why we're not making you find the range. So last year we made people find the range. You would have to know exactly what this maximum point is, and you would have to know exactly what this minimum point is. And you can only do that on the calculator. Do you remember doing this? Let me show you something. So the maximum actually occurs right here. I'd have to do second trace, calculate a maximum, and I'd have to go to the left of it, right there. And then I'd have to go to the right of it, right here. Okay, and so here's what it says my maximum is. But watch, here's where we ran into trouble. So we said, okay, so our range is going to be from negative infinity up to negative 0.65 inclusive. Can you guys think of why this is a problem?
Because it's asymptote?
No. If you don't have a calculator, that would be a problem. But what's even the problem with me saying that this is the answer for this part of the range? Yeah, Tom. Exactly. Nice job. We have done several of these problems last year, and the valedictorian of last year's class was the first person to say, wait a minute, we can't really say that because we're saying, when we write this, we're saying we don't go any further than negative 0.65. That's where we stop. Do we really stop at negative 0.6? We go a little bit higher than that, don't we? Because we're rounding this number. And that's why Mrs. Green and I decided, all right, we're not going to deal with that because we're really talking about this answer is not exactly right. See what I mean? And it's impossible to make it exactly right. Even if you write out all these digits, it's still not right, is it? Because it keeps going even a little bit higher than that. So that's the reason we're stopping with the range, is because of that little tiny glitch with it. Okay? All right. Good job, guys. I know that was a lot.